Hi, because of the coronavirus, it's getting out of hand, and so we're changing everything online. I'll try to explain things to you clearly, and but now I want to be covering things that I have done in the classroom quickly to reach the point I want to show you, and we're in chapter 13, and we have started the first section, and we have finished the preparation of the Anova table. Okay, and the first part of the Anova analysis of variance methodology, and the first part is to conduct the test to see whether the population means are the same. Okay, there are basic requirements for this framework, the framework of the analysis of variance methodology. And the first one is that we are comparing the population means from k different normal populations. Okay, and the basic requirement for this method, there are three. The first one is that the samples are independent random samples from the population. And the second one is that the populations are all normal. And the third one is that the population variances are the same. Okay? And the methodology, the layout of the data. There are two possible resources of this kind of data. The first one is from an experimental study, and the second one is from an observational study. And but anyway, the analysis, the method will be the same. So I want to, I want to skip the explanation of the experimental and the observational study. And we have covered the computation of the total sum square, error sum square, and the treatment sum square. And we have come to the preparation of the table, Anova table. And this is the table of the example in the book, right? The numbers are pretty good. And the F test, we calculated the F ratio. The ratio of the two mean squares 9.18, and using the corresponding degrees of freedom, we can do the t-test. And the t-test, find from the table the critical value, and 10.75 is greater than 3.10. And yeah, this is the second example. The first example actually is 9.18 using 212 degrees of freedoms. Okay, and the first step to test to see whether the means are the same, we have done it, and it is recommended, it is suggested that you work on several exercise problems to familiarize yourself to the method. Okay. There is one particular case when k is 2. When k is 2, okay? But really, the data can provide you with sufficient information to prepare, to complete the Anova table. So you get to complete the Anova table and carry out the F test. And for this k equals 2 case, when there are only 2 treatments, you don't have to do anything more. But when k is greater than 2, as I said in the classroom, The first step, you want to make sure that the means are the same. If the null hypothesis saying that the means are the same is rejected, the null hypothesis saying that the means are all the same is rejected, then we have to go into the details and find the largest or the smallest if necessary, of the population means. Okay, and so there is a second step. But however, when k is 2, then the second step is not going to be necessary, because when k is 2 and the null hypothesis that's saying that the means are the same is rejected, then we know which one is higher and which one is lower, smaller. Okay? And of course, I want to show you that when there are only 2 treatments, the other method, two sample t-test, 2 sample t-tests are also available, and the result, and this file will be provided to you, and this file will be uploaded to Moodle, and you get to download it, and look what happened here. And there is a one-to-one correspondence. There is a one-to-one correspondence between the result of the 2 sample tests and the 2 sample t-test and the Anova. Anova, we're talking about f-test. In Anova, we're talking about f-test. In 2 sample t-test, we're talking about what else? T-test. And there is a exact relationship between the f-test and the t-test, and which is f equals t squared. F equals t squared, and it goes the same. It goes the same for the critical value. The critical values carry the same relationship. Okay. Yeah, I want to repeat this because this is very important. I want to repeat this part now. From the above example, we found that the SSE error sum square is actually the weighted sum of sample variances. The MSE is actually the pooled estimate of the common population variance sigma squared. This is super important, okay? Super important. We denote it by sigma square hat equals MSE. Sometimes this symbol is also used SP square. It says that the estimate for sigma square is MSE, or equivalently SP square if you use. I believe in our book this symbol is also used. And then after the preparation of the Anova table, here comes the topic. We want to estimate the parameters. Now remember here, what are the parameters? There are means. There are k means, mu1, mu2, up to mu k, k means, and there is this sigma square, and sigma square, and then nothing else. Okay, k means and the sigma square, and we have put sigma squares aside because we have established the estimation of sigma square and simply use MSE. The following statistical inference, we need sigma square because sigma square is no longer given. It will be estimated, and only through estimation. But however, it's not a problem because we have this estimate whenever the Anova table is prepared. Okay. If you want to estimate the mean, the estimator is the sample mean, is the treatment mean, and the treatment mean follows the distribution because it's normal. Well, I wonder if you have noticed that the sample size is quite small. Yeah. But however, we do have normal population, so small sample size really doesn't hurt at all. Okay, we have this um, normal distribution and the critical the interval, the critical the confidence interval is like this. Okay, the confidence interval. But however, the confidence interval for each individual sample mean is not it's not important because we the question what the sample mean is really not of interest to anybody because you see the battery example, we want to find the largest number, the largest number of the average life, and the first one method, different method of producing product. We want the largest number and nothing else. And no matter what the largest number is, we're going to take it, no matter how large or how small. So we're not actually interested in knowing the estimate for the sample mean. Okay. And so, but however, we want to compare to get the result, which is the largest, which is the smallest. So it is more of interest to us to compare the two. Okay. We want to establish the confidence interval between mu I and the mu j. Say any pair of the two estimate of the any pair of the means. We will compare and finish ordering them in terms of magnitude. Which one is the highest? Which one is the smallest? Okay, according to the rule, we have the estimate and the estimate put in here, and okay, this is our confidence interval. And using the example of the battery, if we want to compare the first and the third, we want to compare, and then the computation says that it eventually is 15.5 plus or minus 6.8. Okay, 6.8 actually is a threshold. Is a threshold. You see the difference, the nature of the number. The nature 14.5 is actually the difference, and the 6.8 as compared to 14.5, it determines whether 0 is in the interval. I have told you about this 0 thing, and 6.8, if it's smaller than 14.5, then 0 is not going to be in the interval. If this margin of error is greater than this number, and that is to say the difference is smaller than the margin of error, and 0 is going to be in the interval. When 0 is in the interval, we say that they are not significantly different. So eventually, this serves as a minimum significant difference, and we compare the difference, each difference to this number. Okay?